Hi, in this video we'll talk about the WBG, we'll explain that in a minute, a bootstrap method in order to test for trend. Recall in the last video we had talked about the standard t-test method in trying to detect whether or not there's a trend, a permanent trend in a data set, and we saw how poorly that it behaved. Since then, you've learned about the Cochrane-Orcutt, and that's another method that was used to alleviate some of the issues that the standard t-test had, and we'll talk about that in this PowerPoint presentation as well. So let's go ahead and go over there now. So this again is a QR code 8.3 in chapter 8 still, and this is called the Bootstrap test for trend. And that's what we're going to learn about here. Let's review really quickly. Speaking of that previous video, a good way to warm up here and get ourselves prepared for the bootstrap test is to look and see what's already happened. And remember that we talked about the standard t-test simulations, and the relevant questions were, how often does the standard t-test detect a trend? I put that in quotes because it's not a real trend in a stationary AR1 realization, which we discussed back in that video. If it's stationary, there is no time-dependent trend. We know that. So the question is, how often does the standard t-test say that there is? Incorrectly say that there is. That would help us then know how important that uncorrelated assumption was whenever we first learned about the standard t-test, SLR standing for simple linear regression. So that's what we did, and we saw these terrible results. First of all, let's talk about the actual model. Remember, the actual model is xt equals 10 plus zt, where zt is a zero mean AR1 with these four different phi1 values of 0.8, 0.9, 0.95, and 0.99. Those all imply that this is a stationary model because in absolute value, those are less than 1. And then what we did was we simulated 1,000 realizations with length n equals 100, 200, and 500, giving us 12 different combinations. We generated 1,000 realizations from each of those 12 combinations, and then we tested this hypothesis that B1, that's the slope coefficient, is equal to 0, or whether it's not. Now, again, we know the truth, the actual truth is that there is no linear trend present because this is a stationary model. So the question was, how many times did we reject that null? And if we're setting our nominal significance level to be 0.05, we hope that our observed significance level is also around 5%. And what did we find? We found that it was terribly high. So we have huge numbers here. We were hoping these values would be around 5%, and they're not. And the closer that the phi1 value gets to the unit circle, the worse it gets. And we said then that we need a new test that's going to adjust for the correlated errors, because that's the thing that's causing trouble here. The standard t-test assumes that you've got uncorrelated errors. You've got independent errors. But we know in time series data sets, a lot of times we do not. In most cases, we do not. So we need a new test. So that's when we learned about the Cochrane-Orcutt test. And the Cochrane-Orcutt test was a very popular test that was developed by these two researchers. And it is an improvement. There's no doubt about that. So we ran simulations under the same setting. We've got that same AR1 model with those same phi values and checking it at n equals 100, 200, and 500. Let's take a look really quickly. For phi1 of 0.8, notice that our values are 15%. We're hoping these are at 5%, but we've got 15%, 10.8%, 7.5%. Well, that's a whole lot better than this slide, where it was in the 50s, 15, 10, and 7.5. But notice that we're still not down to our 5%. The 7.5% is not bad. But notice that was for a higher realization length. For n equals 100, 200, and 500, it appears that the observed significance level is decreasing. And that holds true throughout the table. If you'll take a quick look across the numbers there, there's something to that. We'll talk about that on a later slide. What about phi1 of 0.9? Well, the numbers jump up some, 21, 12, and 8.8, but better than the slide before when it was in the 60s. So yes, Cochrane-Orcutt is an improvement. 21.4, 12.9, 8.8%, better, but not down to 5%. For phi1 of 0.95, 32, 20, 11, better than the slide before when it was in the 70s, but not nearly 5%. And then at phi 1 of 0.99, we've got really high numbers. So yes, Cochrane-Orcutt is an improvement. We talked about that method in detail in the last video and in the textbook. And it's not bad. We showed the code for it too, the TSWGE code. It's not bad, but we would like to improve on it. And that's what brings up the topic of this video, where this is called the Bootstrap test. And I mentioned earlier that it's the WBG Bootstrap test. What does that mean? Well, it refers to our first author, Woodward, who worked with two other researchers, Batone and Gray. Buddy Gray was a longtime researcher at SMU in time series. Woodward and Gray did a lot of work together. And back in 1997, they came up with this method called the WBG Bootstrap test for trend. The details are in section 8.1.1.4. You can go look at that if you would like to. And the good news is its basis is really the Cochrane-Orcutt methodology, and I went into detail on that in the last video. It just has an extra little step, and that extra step is the bootstrapping step. And bootstrapping is a resampling procedure that is often used to improve estimates of the order P and the parameter estimates by Berg estimation. Berg estimation is used because of all these resampling iterations that happen. There's a bunch of there's a lot of calculation that's going on, and Berg estimation is quicker. It happens quickly, more so than MLE. Remember, it also gives you a stationary solution, so there are some advantages of Berg estimation. So that's how this procedure was developed. Okay, let's look at results. Remember, we're hoping, because the nominal significance level is 0.05, we're hoping for values around 5%. Our first two tables have not been near 5%, and take a look at this, and we're talking over in phi 1 of 0.8 column, 4.7, 4.2, 4.6. For phi 1 of 0.9, right in the 5 range. Phi 1 of 0.95, 7.4, 5.5, 5.5, and at phi 1 of 0.99, a little higher than 5, but not bad, and way better than anything we've seen before. So this is a quite impressive result and research discovery by Woodward, Batone, and Gray, and that is why we recommend this procedure in order to test for linear trend. So here's an interpretation of the results. The WBG Bootstrap test was extremely adept at rejecting the null when it should have. In this case, that is the case of this AR1 model for phi 1 of 0.8, 0.9, 0.95, and 0.99. And how often was that? About 5% of the time, because we set the nominal level to be 5%. So what does this mean? Well, that means that when this test, as opposed to the ones before, when this test says there is an upward or downward trend, then the good news is we can believe it. The good news is the trend is likely real and probably not just some temporary pattern that's about to change in the future. Now, here's the cost. The cost of this test is that it's not as powerful as the standard t-test or the Cochrane-Orcutt. Why not? Remember the definition of power. Power is the probability of rejecting a null when it is false. And that's a good thing. You want to reject the null when it's false. Well, we're not surprised that the standard t-test and the Cochrane-Orcutt are more powerful than WBG, because why? Well, the problem with those tables that we saw was that those two tests were rejected, especially the first one. The standard t-test was rejecting the null left and right. It was rejecting the null in all kinds of cases. More than 50% of the time, it often rejected the null. Well, if it's often rejecting the null, it's probably going to have high power, because the power is the probability of rejecting the null when the null is false. Well, if a test is rejecting the null all over the place and just seemingly all the time, well, yeah, it'll probably reject the null when the null is false, but it also rejects the null when the null is true. So there's that give and take thing about the power and alpha. So not the first time we've run into that, but that is the cost. But we think that that's better than a test crying wolf. And by crying wolf, you saw us write that in the text, meaning that a test like the standard t-test or even Cochrane-Orcutt, which more often than it should says, oh, there's a linear trend and it's a real trend and it's permanent, when the truth of the matter is it's not. So that's what we mean by crying wolf. There are some competing methods. Beach and McKinnon in 1978 proposed a maximum likelihood based method. Very popular authors, Copperthwaite and Metcalf in 2009 proposed a generalized least squares method, GLS method, that is not bad. Neither of these are bad, but we've shown by simulation results that they're not as good as the WBG Bootstrap for AR1 models with phi1 greater than 0.9. When phi1 is greater than 0.9, that's where things get tricky, and it's easy for other tests to not do as well as this test does. One other thing, I mentioned realization link just a little bit ago. Let's talk about that. You saw in that table for the Cochrane-Orcutt and also for the WBGE that the longer the realization length, the better the test does in being accurate about rejecting the null when it should. And so a fact that in 1997, when Woodward, Batone, and Gray did their work, they showed in that paper that for a stationary AR1 model with phi1 greater than 0.9, it may require realizations as long as n of 1,000 or longer to achieve the observed significance levels close to the nominal levels that they were supposed to calculate. So, and that's bad. I mean, if it's taking realizations that long, I mean, that's requiring a lot. Having a realization as rich as n of 1,000 or longer, that may not even be possible. And that's why this is viewed as a negative, because if it's taking that long of a realization in order to get the observed significance level to be close to the nominal level, that may not even be possible. And that's why this WBG test is a great improvement. So here are our conclusions. When determining whether a time series dataset has a trend, and I said to begin with, this is a hard question, use the WBG Bootstrap method for two reasons. Number one, we saw in our simulation results, it does a really nice job of controlling the observed significance levels and keeping them close to the nominal levels, especially when compared to the standard t-test and Cochrane-Orcutt even. And secondly, because of our TSWGE package, we've made it really easy to do that in practice in R. The function is wbg.boot for bootstrap.wge. So I hope that you found that interesting. That's really a neat takeaway, a very great discovery by Woodward, Batone, and Gray, and gives you a method to test for trend, and you're going to see how that's important when you model a real time series data set in future examples.